So, we will continue with our introduction to boundary layers and the different concepts which are involved in this, and I will refer back again to our previous discussion, in which we have seen that wherever there is a flow over a surface, over a solid surface, all the transport phenomena is going to be confined in a region very close to the surface. Beyond that region, the flow will move unhindered, unaware of the presence of the solid below, and in that region the flow can be treated as inviscid, that is without any viscosity. However, in the region close to the solid surface, where the velocity will vary from that of the solid plate, that of the solid surface, to the free stream condition, is known as the boundary layers. So, the concept of boundary layer, which was the missing link between theory and experiments while designing the shapes, was introduced by Prandtl, and what he has shown is the layer of inviscid fluid and the layer of where the viscous forces are important. And the concepts find widespread use in the design of any moving object, be it a car, motorbike, cycle, bus, aircraft, and so on. And also in the field of sports, intelligent use of the formation of boundary layer can make a person do wonderful things while bowling, while playing any other games, baseball, and so on. So, we are going to have our structured study of boundary layer in the coming classes, but first of all we have to define what is the thickness of boundary layer, because that is of paramount importance. If we need to know, how do we know that up to this distance the effect of viscous forces are present, and beyond that point the viscous forces are not present. So, we use the velocity at that location to be a pointer to decide whether or not we have hit the edge of the boundary layer. So, the problem is that the velocity varies from that of the solid object to that of the free stream, and by free stream I mean where the fluid is free of the viscous forces. Okay. So, they vary asymptotically. That means the velocity, the gradient of velocity with y slowly decreases, the gradient of velocity in the x direction with y slowly decreases, and the profile is something that I have drawn over here. So, the profile of the boundary layer is something like this. So, if I can draw the velocity in here, the velocity profile, it is going to start at a value equal to 0, and then this is your approach velocity, which is denoted by v, and over here I have the free stream velocity, which is denoted by u infinity. That means the velocity in the x direction at a distance, at a very large distance from the plate, this is the x direction and this is the y direction. So, inside this boundary layer, the velocity in the boundary layer is in the x direction is a function both of x and y, and outside the boundary layer the velocity is simply going to be a constant equal to the free stream velocity. So, it is 2D flow inside and it is inviscid flow outside. For this special case of flow over a flat plate, the approach velocity is equal to the free stream velocity. But in order to keep our discussion general, we will refer to the point at which the velocity inside the boundary layer becomes equal to the free stream velocity. We call that as the thickness of the boundary layer, generally denoted by delta. So, delta is the distance over which the velocity changes from 0, relative velocity 0 on the solid plate, or the velocity of the solid plate, to the velocity of the free stream. This is what delta is. But if you look at this region, the nature at which the velocity approaches the free stream velocity, it's asymptotic in nature. So, where I am going to draw the line, is it this point where it has become equal to u infinity, or is it this point at which the velocity becomes equal to u infinity? So, each person probably will decide on the velocity, the location at which the velocity becomes equal to u infinity in a slightly different fashion. So, the common practice of the boundary layer thickness is it's the thickness at which the velocity, that is Vx, is equal to 99% of the free stream velocity. So, y at which Vx is 0.99 u is called the boundary layer thickness. So, this is the standard definition of boundary layer thickness. It is also called, sometimes it is called the disturbance thickness. Because this is the extent to which the liquid fills the presence of the solid plate below it. So, it is also commonly known as the disturbance thickness. But even then, it's not a foolproof method. That the fact that where the location where the velocity is 99% of the free stream velocity is also prone to error because of the nature of variation of Vx with y. So, I understand that Vx is a function of x and is a function of y. However, near the boundary layer, del Vx by del y approaches 0. That means, beyond the boundary layer, Vx is not a function of y, Vx is not a function of y anymore. So, these are mathematically the definition of the location of the boundary layer, but it is so difficult to theoretically pinpoint where this happens. So, each one of us probably will decide that, well, this is the location of the boundary layer, and we are also going to use some sort of a measurement technique, a device, an instrument to demarcate the point where the velocity is 99% of the free stream velocity. Each of these instruments, they have errors associated with it. Each one of us will make some errors, the human error. So, these errors, taking into account of these errors, the final error in the evaluation, in the determination of the boundary layer thickness is extremely difficult and is prone to large errors. The problem comes more because we are trying to measure the velocity at a point or at every point, and then try to project that to some sort of a thickness, some sort of a disturbance thickness. This is a differential approach. Any differential approach is prone to experimental error. So, there is an alternative method. If you try to think of an alternative method which is integral in nature, then that would probably give us a fairly decent error-free measurement of some sort of a boundary layer thickness, and that is what we are going to see next. So, the next approach is known as the displacement thickness. So, what is displacement thickness? That is what we are going to find next, and it is generally denoted by the symbol del star. Okay. So, we would see what it is. When I have flow in this, the mass flow in this region where the velocity is moving with the free stream velocity is going to be more as compared to this case where the velocity, where the fluid is moving with Vx, or in some cases is also denoted by small u. So, Vx is the x component of velocity, or which is also denoted by u. So, over here the fluid is moving with u, over here the fluid is moving with Vx or u, and u is definitely less than capital U. The flow inside the boundary layer is less than the free stream condition. So, the amount of mass which travels through the boundary layer is less than that of the free stream. So, how much of less mass that we are going to have inside the boundary layer? The amount of due to the influence of viscous forces, the amount of mass would amount of reduction in mass flow rate in a boundary layer would simply be equal to 0 to infinity rho times capital U minus small u times dy. Here we have assumed that the depth perpendicular to this paper is unity. So, if I did not have the boundary layer, the amount of mass flow rate would simply be rho u times dy. Since I have a small u present in this part of the film, so this capital U minus small u denotes the reduction in the mass flow rate as a result of the presence of viscous forces in it. So, if I integrate it from 0 to infinity, though I understand that I do not have to integrate it from 0 to infinity, I can simply integrate it from 0 to delta, because by definition small u becomes equal to u once you cross delta. But anyway, in order to keep the generality, we keep this definition, which gives me the reduction in mass flow rate inside a boundary layer. So, this denotes due to the presence of the boundary layer. Now, let us say that I would like to get the same reduction in the case of inviscid flow. So, this is viscous flow, and I am imagining an inviscid flow in which I would get the same reduction in mass flow rate. So, I have a plate, I have the motion, I have the formation of the boundary layer. Inside the boundary layer, the liquid moves slowly as compared to the free stream. So, the reduction in mass flow rate is simply going to be the difference in velocity between these 2 points multiplied by rho multiplied by area. So, area is fixed width or unit width, and this length scale is simply going to be 0 to infinity to be more correct, mathematically more correct, or 0 to delta, the thickness of the boundary layer, to make it practical. So, this is in viscous flow. The liquid slows down. Now, let us think of that the entire fluid flows over the flat plate, but this time the fluid is inviscid. But I would like to have the same difference in mass flow rate as in the case of viscous flow. So, in order to reduce the flow of fluid over the solid plate in inviscid flow, the only option available to me to reduce the flow rate is simply by restricting the flow area, simply by putting the solid plate up by a certain distance. I restrict the flow area, and therefore, whatever was flowing below, whatever was flowing on top of this by which I have raised it, that area is no longer available to the flowing fluid anymore. So, in an inviscid flow, if I raise the solid plate by a distance equal to delta star, then I am essentially making that much of area unavailable to liquid flow. So what is the area which is unavailable to liquid flow now? One is this delta star multiplied by 1, because I am talking about unit depth. I have taken unit depth. So delta star amount of area, this delta star times 1, this is no longer available to flow right now. And what is the mass that is moving through this, that would have moved through this area, delta star multiplied by 1? The mass which would move through this is delta star multiplied by 1, which is the unit depth, multiplied by the velocity with which the fluid was supposed to flow through this. What was the velocity with which the fluid was supposed to flow through that blocked area? Since it's inviscid flow, the velocity everywhere is u infinity. So if I raise it by a distance delta star, the amount of area that I have blocked, the velocity of the liquid through that area would have been same u infinity, since it's inviscid flow. So by raising it up by a distance delta star, the volumetric flow rate reduction is simply going to be area times the velocity. Area is delta star into 1, and the velocity is going to be u infinity, the free stream velocity. It's an inviscid flow, so there is no question of any change in velocity. So the volumetric flow reduction on account of raising the solid plate by a distance delta star would be u infinity times delta star times 1. What is the corresponding reduction in mass flow rate? Simply multiply it by rho. So the mass flow rate reduction, because of my raising the platform by a distance of delta star in an inviscid flow, would simply be rho times del star times 1 times u. When the reduction in mass flow rate in the inviscid flow is going to be equal to the reduction in mass flow rate in the actual viscous flow, that we have the expression for which we have already evaluated, when these two are equal, delta star is known as the displacement thickness. So let's see what is the amount of reduction in mass flow rate in a boundary layer where viscous forces are present is this. Now in an inviscid flow, the reduction in mass flow rate, as we have decided, as we have discussed, is going to be rho times u times delta star when the platform is raised by a distance which is delta star. So this is the reduction in mass flow rate in an inviscid flow when you raise the platform by del star. When these two are equal, this delta star is known as the displacement thickness. So what is going to be the final expression of delta star? Delta star would simply, it's an incompressible fluid, so rho will simply cancel out. So it is from 0 to infinity, and if I divide it by capital U, 1 minus small u by capital U times dy, or it can be, practical purposes, it can be equated to 0 to delta, because nothing happens beyond delta, by u into dy. So this is the definition of this displacement thickness. Now if you look carefully over here, the delta star, the displacement thickness can be expressed, since it's an integral thickness, it can be expressed as a sum of, it can be expressed as a sum of many such terms. Now the problem that we had in evaluating the correct value of delta is right over here, where the flow, where the velocity essentially asymptotically merges to that of the free stream. What happens to those summation terms when we reach delta? As I reach delta, u starts to become close to capital U, and therefore the contribution of the terms near delta, the contribution of all these terms near delta essentially becomes insignificant. So, the integration has been provided, the integration has provided us with an opportunity in which the integrand vanishes in the free stream or near the free stream. Since most of our errors were associated with the evaluation of the exact velocity near the free stream, here we have a method in which the integrand itself vanishes near the free stream. So, therefore, any possibility, any error that you may have in the correct evaluation of velocity at a distance close to that or near to that of the free stream, the effect of that error will be insignificant in the final form of delta star. So, that is why that is the beauty of an integral thickness over a differential approach over delta. So, delta star is going to give you much more accurate value with enough confidence as compared to delta, which is differential in nature. So, displacement thickness are always safer to use than the boundary layer thickness or the disturbance thickness. Even then, people still use boundary layer thickness delta or the disturbance thickness delta, because it gives you a nice pictorial view of what happens inside the boundary layer. Inside the boundary layer, the velocity changes from 0 to that of the free stream. It gives you a picture which is very easy to understand. On the other hand, it is prone to error, but the alternative delta star is integral in nature. You need to know the concept before you can truly appreciate the usefulness of delta star. So, the more common representation of boundary layer they are always in terms of delta, not in terms of delta star. But if you go for some accuracy, and we would see later in our subsequent classes that we use delta star as well in our calculations. There is one more definition which we need to cover before we close this class, which is known as the momentum thickness. Which is denoted by the symbol theta, and the momentum thickness is also an integral thickness. And what we do is, we are first going to find out what is the actual flow that is taking place inside the boundary layer. So, the actual flow which is taking place inside the boundary layer is integration rho times u times dy, where y varies from 0 to infinity, and y is 0 to infinity, the infinity is put to mathematically, because only at the infinite distance the velocity becomes equal to the free stream velocity. But we artificially put a condition where the velocity reaches 99% of the free stream velocity. So, we can later on convert this integral to 0.99 or all. So, when you think of the flow inside the boundary layer, we are trying to find out what is the mass flow rate. So, the mass flow rate must be equal to integration, since my small u is a function of y. So, I must integrate. Okay. So, rho times u dy, y varies from 0 to infinity. That is going to be the amount of mass flow rate inside the boundary layer. What is the reduction in mass flow rate of this amount of flow because we have a boundary layer, because we have viscous flow? If this amount of fluid given by integration 0 to infinity rho small u dy, had this been moving in an inviscid flow, it will have a momentum associated with it, and in order to find the momentum, I must multiply this mass flow rate with the prevailing velocity. So, the velocity in inviscid flow is simply this mass flow rate multiplied by capital U or u infinity, where u infinity is the free stream velocity. So, the mass of fluid that actually flows through the boundary layer, had it been moving in an inviscid flow, it would carry a momentum which would be equal to integration 0 to infinity rho u small u times capital U dy. But it is not moving in the free stream condition. It is not moving in inviscid flow. It is moving in viscous flow. Since it is moving in viscous flow, its velocity is not capital U, its velocity is small u, and we understand that small u is a function of strong function of y. So, what is the reduction in the mass flow rate of in this quantity of fluid because we have a viscous boundary layer? The mass is rho u dy, rho small u dy. What is the reduction in momentum because of the presence of boundary layer? So, that is what I am going to write here. So, I must multiply this with u infinity minus small u. So, u minus small u, this is giving me the reduction in mass flow rate, reduction in momentum flow of this mass. So, this gives me the mass and this is the reduction in velocity. So, together this integrand gives me the reduction in momentum for the fluid that actually flows. In the boundary layer. So, this essentially is then the reduction in mass flow, reduction in momentum for the fluid that actually flows in the boundary layer. Now, I would like to do it, I would like to, as in the previous case, I have evaluated what is the reduction in mass flow rate of the actual fluid that flows in the boundary layer. Now, I am trying to see what I have to do in order to what do I have to do in an inviscid flow to get the same reduction in momentum. I have a flow, some amount is flowing over this. I understand that the reduction in momentum is what we have decided. But I need to do something with the flow area such that the reduction in mass, reduction in momentum flow in an inviscid flow is exactly the same as in the momentum that we have derived in previously. So, what I do is I raise it by a distance delta star. I raise it by a distance theta, sorry, I raise it by a distance theta. Whenever I raise it by a distance theta, some amount of area is no longer available for flow, which would result in a reduction in mass flow rate. So, let us see what that is going to be when you raise the platform by a distance equal to theta. So, when you raise it by theta, the reduction in mass flow rate is simply going to be rho u times theta. So, and I am again assuming that the depth is equal to 1. So, theta times 1, the unity is already there. So, u times the area multiplied by the rho gives me the mass flow rate that an inviscid flow would on a solid plate. This would be the inviscid flow of mass over it. What is the momentum associated with it? Another u. So, this is the mass flow rate and this is the velocity that would have existed in an inviscid flow. So, the inviscid flow reduction in momentum, since I have raised the platform by a distance theta, is this. So, this is the reduction in momentum in inviscid flow. So, this is the reduction in momentum of the actual mass of fluid that passes through the boundary layer, and this is the reduction in velocity. So, this is the reduction in momentum for the fluid that actually flows through the boundary layer, and when I write is rho u square theta, this is reduction in momentum in inviscid flow when you raise the platform by a distance equal to theta. Theta is called the momentum thickness when these two are equal. So, theta is termed as the momentum thickness when the reduction in momentum flow in an inviscid flow case is equal to the reduction in momentum of the actual mass flow that is taking place in a viscous boundary layer. So, with this, as previously, we can obtain an expression for theta as 0 to infinity small u by u infinity 1 minus small u by u infinity dy, or which for all practical purposes can be approximated by 0 to delta small u by u infinity 1 minus small u by u infinity times dy. So, this is what you would get when you this is what is the definition of the momentum thickness. So, momentum thickness, as in the case of displacement thickness, is also an integral thickness, and the integrand vanishes in the free stream. So, momentum thickness will also be able to avoid the errors associated with displacement thickness or normal boundary layer thickness if we use either the momentum thickness or the displacement thickness. One denotes the reduction in mass flow rate because of the presence of boundary layer, the other denotes the reduction in momentum because of the presence of the viscous boundary layer. So, these two concepts will be instrumental in our understanding of the theory of boundary layers in subsequent classes.